Hello friends, welcome back to BBSbaba Physics. Today we are going to learn about electromagnetic potentials. तो आप देख सकते हैं electromagnetic potential क्या होता है जो हम देखते हैं phi in electrostatics and there is associated potential which is A that we know that is associated with magnetic field. So let's begin. Electromagnetic potential E and B जो है पोटेंशियल इज व्हाट पोटेंशियल इज स्टेट वेरिएबल फॉर एग्जांपल अर्थ का पोटेंशियल निकालते हैं तो हम इन्फिनिटी पे जीरो मान देते हैं देन वी गेट सम पोटेंशियल सो व्हाट पोटेंशियल इज अ स्टेट वेरिएबल एंड दैट इज व्हाट इट इज पाथ इंडिपेंडेंट इसका मतलब क्या हो गया वी कैन चूज एनी आर्बिट्ररी इनिशियल वैल्यू ठीक है इलेक्ट्रोमैग्नेटिक वी पोटेंशियल होता है प्लस माइनस ये एक्चुअली पोटेंशियल डिफरेंस डिपेंडेंट नहीं होता है इट इज पाथ इंडिपेंडेंट correct and it's a state variable but electric field and magnetic field are not state variables right it depends upon the origin right so now moving ahead b ये बायोट लॉ से एक्सपेरिमेंटल लॉ है b इज इक्वल टू म्यू नॉट बाई 4 पाई आइडियल क्रॉस r बाई r क्यूब एक्सपेरिमेंटल लॉ हम g 1 बाई r को रिप्लेस कर सकते हैं r बाई r क्यूब इसकी जगह हमने वी हैव रिप्लेस दिस ओके सो वी वांट टू डिफाइन फॉर एग्जांपल E इज इक्वल टू माइनस ऑफ डेल फाई हमने इलेक्ट्रोस्टैटिक्स में यूज किया उसी तरह हम चाहते हैं कि magnetic field is something del cross A cross product of A so this is what this is vector potential okay so in terms when comparing these two we'll get to know that A becomes mu naught by 4 pi I dl by r okay so this is vector potential now moving ahead this is third Maxwell equation so what is E is equal to minus of del v when we integrate on the line integral closed line integral E dot el when we start from the point and come to the same point it becomes 0 then in that case del cross E is equal to 0 so this is a case of electrostatics there is no charge moving but del cross E is equal to minus of dou b by dou t this is a case of electromagnetics okay third Maxwell equation when now I am replacing b by del cross A what it becomes del cross E minus del cross A now take this to this side so del cross E minus minus plus dou by dou A is equal to 0 now so this quantity E is what earlier minus of del phi electrostatistics but here E plus dou A by dou T is equal to minus of del phi and this potential is electromagnetic scalar potential this potential electromagnetic scalar potential earlier E is equal to minus of del phi right but here E plus dou A by dou T is equal to minus of del phi because magnetic field is also there so this is called electromagnetic scalar potential now what E becomes this goes this side so this and this is vector potential as said earlier this is electromagnetic scalar potential now we have to see as we have discussed that the potential can have any arbitrary origin and potential is because potential is a state formula it doesn't depend from where you are taking the origin so we can prove this by Gauss invariance what is Gauss invariance by change of Gauss what is Gauss meaning scale by change of scale if the field parameters do not change then it is called Gauss invariance let's see now what we are doing now A and phi electromagnetic potentials are there they are uniquely determined field parameters even if we change A even if we change phi but they determine field parameters uniquely by changing these our electric field and magnetic field does not change arbitrarily for a particular condition so okay they uniquely determine field parameters but they themselves are not unique that is what is called Gauss invariance let's see how we can prove it if I can be arbitrarily chosen okay so A dash we are taking A dash is equal to A plus some function of r and t position and time we are choosing we are adding FRT okay del of FRT okay we can choose arbitrarily similarly phi dash is equal to phi minus dou f by dou t right so B dash is what suppose I am thinking I'm saying that it changes I don't know let's see del cross A dash del B dash is equal to del cross A dash okay so del from in place of A dash we are putting A plus del of F okay so del cross A now this is what del cross del F so what is this this is gradient we know curl of a gradient is always 0 okay so this quantity vanishes So b dash boils down to b. Okay, so b dash boils down to 3. So what it means, that even we have changed we have changed a to a dash, then also b does not change. That is what Gauss invariance in terms of magnetic field. Now the same will happen for the electric field. Now moving ahead, e dash is equal to minus of e, we have calculated minus of del of phi minus of dou a by dou t, right? So e dash will be similar. E dash will be what? Minus of del phi dash minus of dou a dash by dou t, right? Again put phi dash is equal to what? Phi dash is equal to phi minus dou f by dou t. We have chosen phi is equal to minus dou f by dou t, right? A is equal to what? A dash is equal to a plus del f. Okay, so minus of del phi minus minus plus, this is plus quantity, again this is minus, or this is minus minus, so this quantity and this quantity cuts down and it vanishes. So E dash is equal to, again E dash is equal to minus of del phi minus of dou A by dou t, right? Then again it becomes E dash becomes E, right? This both are same. So that is what electric field does not change. So this is Gauss invariance. Gauss invariance, even if the potential parameters have been changed, not unique, but they determine the field parameters uniquely. So this is called Gauss invariance. Moving ahead, now we know from Gauss law del dot E is equal to rho by epsilon naught. Now in this change condition, what is E? E is minus of del phi minus of dou A by dou t rho by epsilon naught, right? So del dot del phi, we have taken the minus this side, we have taken the minus this side, so minus rho by epsilon naught. So okay, so we have taken the minus this side, so minus rho by epsilon naught del of del dot A, del, or we can exchange, for example del dot dA dou by dou t, we can write dou without any loss of generality. So dou by dou t del dot A, dou by dou t del dot A minus rho by epsilon naught. So what is back on del dot del phi is equal to del 2 phi dou by dou t del 2A del dot A minus of rho by epsilon naught. Okay, so A and phi can be arbitrarily chosen, as we have already discussed. A is chosen in such a way that, for example, this is the we got this equation. Now we can choose a and phi according to our need. So मैंने a ऐसे चुना कि del dot a becomes 0. If that happens, if del dot a becomes 0, then what we get? Del 2 phi is equal to minus rho by epsilon naught. Poisson equation आ गया जो electrostatics में पढ़ते हैं. Phi satisfied Coulomb Gauss in electrostatic potential. Coulomb Gauss in electrostatic potential. In electropotential, what is the del 2 phi is equal to minus rho by epsilon naught. Okay, so this is called Coulomb Gauss because it reduces to Coulomb potential. This condition del dot a, what we have, this is Coulomb Gauss condition. We have put del dot a is equal to 0. This is called Coulomb Gauss condition. Why we are calling this? Because the because it reduces to Coulomb potential, right? Again we are writing the first equation. Now earlier we have in Coulomb Gauss, what we did, we del dot a is equal to 0. Now we are exploring this equation further. Now add this quantity 1 by c square minus dou 2 phi by dou t2. We have add and subtract, we have subtracted, we have added, koi problem nahi hai, right? So we are combining this together, this quantity together, and taking dou by dou t outside, dou by dou t del dot a 1 by c square dou by dou t लिख देंगे तो dou phi by dou t, right? Now we are what we are doing the Lorentz Gauss Coulomb Gauss condition where del dot a was 0. Now we are extending our argument. Now we are telling not del dot a but del dot a plus 1 by c square dou phi by dou t is 0. If this happens, this is called Lorentz Gauss condition. So this is called Lorentz Gauss condition. So if this becomes 0, then this quantity becomes minus rho by epsilon naught. That is what del 2 phi minus 1 by c square day 2 phi by day 2 is equal to minus rho by epsilon naught. So what we can write, this is, see, this is D'Lambertian, right? Del 2 minus 1 by c square dou 2 by dou t2. We have also proved that D'Lambertian is invariant in our STR lecture. Now moving ahead, so del 2 phi is equal to minus of rho by epsilon naught. Now we have to, let's explore further. Now take the fourth Maxwell equation. Del cross B is equal to mu naught J. This is conduction current density plus epsilon naught dou E by dou T. This is fourth Maxwell equation. Now replace B by del cross A. A is the vector potential. Now mu naught J, mu naught epsilon naught. Putting the value of E is what? Minus of del phi minus of dou A by dou T, right? So we are putting this value from here. Mu naught J and c is equal to what? C is equal to 1 by root and the mu naught epsilon naught. So mu naught epsilon naught becomes 1 by c square, right? So we are putting this same value minus, if we have taken the minus here, so 1 by c square dou by dou t minus of dou by dou t del phi minus of again minus 1 by c square del 2 a by dou t2, right? Now this is an identity. We can use del cos. Del cos is equal to what? Del of del dot a minus of del 2a, right? This is an identity. We know this. Del cos a is equal to del of del dot a minus of del 2a. So putting this, we are substituting this by this. Put this del of del dot a minus of del 2a is equal to what? Mu naught j minus of 1 by c square dou by dou t del phi 1 by c minus 1 by c del dou 2a by dou t2. Now we have to apply what? Lorentz-Gauss condition. We are applying Lorentz-Gauss condition. Okay, by applying Lorentz-Gauss condition. So what was Lorentz-Gauss condition earlier? Del dot A is equal to 0 Coulomb Gauss. This is Lorentz-Gauss 1 by c square dou phi by dou t is equal to 0. This was Lorentz-Gauss, right? This was Lorentz-Gauss condition 1 by c square dou phi by dou t del dot A 1 by c square dou phi by dou t. Now see this, they in this equation the Lorentz-Gauss conditions can be applied. See the white mark thing. Del, we are taking the del dot A and put this comes this side, then 1 by c square del is already there, I am putting it outside, so 1 by c square dou phi by dou t. This is what? If we put 0, we apply Lorentz-Gauss condition, then this becomes 0. Then what happens? What are the left quantities? Minus of del 2f, this is minus of del 2f, this is mu naught j will be as it is, and minus of 1 by c square del 2a by del t2, right? So this has become 0 by applying Lorentz-Gauss condition. So what it remains is del 2a, del 2a goes this side, del 2a, and this remains this side, minus of del 2a minus 1 by c square del 2a by del t2, and this goes this side is equal to minus of mu naught j. So again we see that this is the Lorentz D'Alembertian over del 2 minus 1 by c square dou 2 by dou t2 is equal to what? Minus of mu naught j. So obtain two condition. Del 2 phi is equal to minus of rho by epsilon naught, del 2 a is equal to minus of mu naught j, where j is what? Conduction current density. This is called D'Alembertian electromagnetic equation. इसके solutions जो होंगे, that is will solution is retarded potentials. Now when we got this condition, just to revise that Lorentz-Gauss condition applied, we got this. So I will just summarize. Del dot A is equal to 0 was Coulomb Gauss, because we are getting the del phi is equal to minus of del 2 phi is equal to minus rho by epsilon naught. Coulomb conditions are Poisson equation आ रहा था, and del dot A plus 1 by c square dou phi by dou t is equal to what? Lorentz-Gauss condition. So this is the end of the video. Thank you for watching. Thank you very much. We'll be coming with relativistic electrodynamics and field tensor. Thank you very much.